welcome. We're going to go through kind of a complicated situation of what was happening. So this is going to be, this is a chart that was posted in December of 2021 by John Byrne Murdoch of the Financial Times. And what was happening at this time, okay, was that so starting really in November of 2021, there was this highly contagious Omicron variant of COVID-19, which started this massive wave of cases in London, okay? And this is shown in the chart. And we're assuming, so let's actually kind of write down these little bits. So we're assuming, just kind of keeping track of the information, the first thing that we're assuming is that T is in months. So we're assuming T is in months. And then the other thing that's going to go on is we're going to assume that the wave started with one case, okay? Which, you know, actually there was an initial case. And so this is kind of another assumption. So we're assuming that T is in months and the wave started with one case. So the wave started with, so this would have been kind of an output. So this would have been one case. Okay, so these are kind of our assumptions so far that we have. And then what we're going to want to do, so here's our task, which is, so we're assuming these things, and then our task is going to be to approximate the equations. So approximate the equations for the wave caused by, so for the wave that's kind of shown, so the wave starting in May, which was caused by previous variants, so caused by previous variants, and that caused by Omicron. Okay, and then that caused by this Omicron variant. Okay, and we're going to assume that this is just growing exponentially, that there aren't other factors that are coming into play, such as, you know, some people already have cases, there's a finite population, there's all these things that come into play that actually would alter, but at least in the early stages, exponential growth is usually a good, you know, approximation until enough people get sick or until, like, you know, distance constraints and things like that are going to actually impact it because each person is infecting the same number of people. Okay, so we're going to start, we're just going to assume that we're going to have, so this is going to equal, and this is going to be P naught, whatever, that's going to be our P initial, right? And then we've got E to the K, which is one of the things we have to figure out because it's our growth constant, to the KT. So this is kind of the equation that we're going to be assuming is actually going to hold here, even, well, it'll more or less hold in the early stages, and then, you know, it doesn't quite continue to hold forever, but it's, you know, a reasonable approximation. Okay, so let's start with kind of the other variant. So let's first look at what happens with the other variant. And what do we kind of have? So, you know, the info that we have to start out is we know that P of 0 is going to equal, so P of 0 is going to equal 1. Okay, and that just is from the fact that we said we started with one case. Okay. The other thing that we're going to assume that we know is that P of 2.5, just looking at the chart, it looks like it's approximately 6,000. Okay. And we note that this is actually our P naught. Okay, so the fact that this P naught equals 1, we can plug into our equation up there. So now we get the equation that P of t is going to equal, and let's maybe put a star next to this, okay? So we're putting that into star, and we're getting that P of t is going to equal e to the kt, right? Because our P naught is just 1, so we're not actually multiplying by anything there. Okay. Now, the next thing that we're going to do is that we're going to use, so now we're going to use that, so use that P of 2.5 is going to equal 6,000, right, to solve for k. So we're going to use this to solve for k. Okay, so what do we get? So looking at this, so P of 2.5 is to put 2.5 into there. So we've got e to the 2.5, sorry, we've got to put 2.5, which is, so we've got e to the, and that's going to be for the time, so we still have our k there that we don't know. So this is going to be k times 2.5, right? And we know that that equals 6,000. Okay, so now what do? We can take the natural log, right? Because this is up, we're trying to solve for k, but it's up in the exponent, and we remember that the exponential and the logarithm are inverse functions, so the way to kind of get rid of the e is to take the natural log of both sides. So I take the natural log of both sides. Actually, let's do this in another color. So let's take the natural log of, and then I've got this e to the, I'm just going to write that as 2.5k. It's a little bit cleaner for me. So 2.5k. So I'm just doing this. I'm taking the natural log of both sides. So I'm going to take the natural log also of 6,000. Okay, so that's going to give me that this, right, these because these are inverse functions, I just get left with my 2.5k, so I get my 2.5k is going to equal, and now this is just the natural log of 6,000, like from there. Okay, and I'm still just trying to solve for k, so I'm going to divide both sides by 2.5, and I'm going to get that k is going to equal, so I have the natural log of 6,000 divided by 2.5. Okay, now I need to actually kind of put this back in. So sub k into here. Okay, so this is like double star, this equation here. Okay, so now I want to sub k into double star, right? And what happens is that I get that P of t is going to equal e to the, so then I have this whole big mess, so I have the natural log of 6,000 over 2.5 times t. Okay, but we kind of remember what we can do when we have a product of exponents like this, right? And so I can actually write this as I would have, you know, to the exponent. So let's just kind of do this. So I have P of t is going to equal, so I have e to that whole mess. So this is the natural log of 6,000 divided by 2.5, right? And then this whole thing is going to go to that tth power, okay? But then This is going to give me, oh, I'm going to have to keep rewriting here. Because what I can actually have here is I can break this one apart also. So this is going to equal, now I've got e to the ln of 6,000. The natural log of 6,000, I can take that to the 1 over 2.5, and then all of that can go to the t, right? But I know what's going on with this in here, right? This whole thing is just going to cancel to be 6,000, right? So now I'm almost there, so I have that this is going to equal 6,000 to the, let's split this whole thing, so I have 6,000 to the 1 over 2.5 power to the t. Okay, and now I can use, and I know that this is approximately 32.5. Okay, so putting all that together, I'm going to get that P of t is going to be approximately 32.5 to the t, right? And interpreting that, what does that mean to us? That means that each month, right? So each month, the cases are multiplied by, so each month, right, I have that cases are multiplied by approximately 32.5. Okay, so that was what was happening before Omicron. Like, that was an earlier wave. This is kind of the situation. And the earlier variants, as people were getting vaccinated, this was helpful. And the earlier variants weren't able to break through that. So Omicron was. So let's look at what happened with Omicron. So Omicron, which was much more successful at actually breaking through the fact that a large portion of the population was actually vaccinated. So now we're going to start with, we again have that our P naught is equal to 1, or P of 0 is equal to 1. And in this circumstance, we're going to have that our P of 1 is going to be approximately 10,000. Okay, already you can see this is happening much, much faster. Okay, so this is not a good thing. So the fact that P of 0 is equal to 1, when we put that into our equation star from up there again, that's going to give us that P, our function is now can be written P of t is equal to, and then we just put in our P naught there as 1, so that just kind of drops out, and we get e to the kt. Okay, and then the next thing that's going to happen is that, so this is like kind of our new equation. I'll put a double star next to that. That's the one that we're working with now, but again, we need to solve for our k. Okay, so we're going to use that P of 1 equals 10,000. We're going to say equals 10,000 instead of as approximately. Okay, to solve for k. Okay, so we'll go ahead with that. So we get that. So on this side, we have the E of, and then we have K, but then we're just multiplying by 1, okay, is going to equal 10,000. Okay. Again, we're going to take the natural log of both sides, and we're going to recognize here that, K times 1 is just, this is just K, okay. So when we take the natural log of both sides, we're going to do that. So we have the natural log of, now we're just looking at e to the k, right, because k times 1 is k. So we have e to the k times 10,000. Okay, and again, because these are inverse functions, I just get that input there. And so I'm getting here that k is equal to the natural log of 10,000, right? Which makes it much easier. So now I want to sub this in to double star. Okay, so what I want to do is, right, I want to sub k equals the natural log of 10,000, right, into this double star. So into, why don't I just kind of write out the whole thing, so double star there. So this is P of t equals e to the kt. Okay, so I'm going to get that P of t is going to equal, so we have P of t is going to equal, and then I have e to the natural log of 10,000 times t, right? And again, we can do this thing where, we have a product in the exponent, so we can do to that power to that power. So this is going to equal, so e to the this, so the natural log of 10,000, and then it's going to go after that to the power t. These are, again, inverse functions. So this is going to give me that P of t is going to equal, right, these are inverse functions, so I just pick out what's on the inside, which is 10,000. So I'm just getting 10,000, just getting, this is enormous, so I'm getting 10,000 to the t, right? So like looking at that for a second, this is insanely different than that one. Okay, so this was 32, might be hard to see this decimal point. That's 32.5, right? These are all decimal points. It's always important to make your, that's divided by, I always forget that the decimal points sometimes get lost. So what is this telling me here? So with Omicron, right, we have that each month the cases are multiplied by 10,000, right? This is my approximation, and here's, right, these were my equations, and then that said with Omicron, each month the cases are being multiplied by, which obviously can't happen for too long. There's like, you're just going to run out of people, or multiplied by approximately 10,000. Well, you run out of people, you also start their geographical things, and then the other thing that ends up happening is that, so Omicron responded at least somewhat to booster shots, and so it became a big push to get people their booster shots to help with this. Okay, so what we did in these examples, we used our initial, the P of 0 equals 1 to stick into here, and then we used the value that we knew, right, and that this is, more or less growing exponentially to solve for k. Using the fact that, multiple times we use the fact that the natural log and e are inverse functions of each other, so you can just kind of pick out what's inside there. And also the other key thing that we use that can get a little confusing to people is that when you have a product in the exponent, right, you can take e to the, the natural log of 10,000 to the t, which then allows us to actually kind of use the fact that these are inverse functions and get that we're multiplying by 10,000 each month. Okay, so I hope that made some sense, and I will see you in the next lecture.